Yeah, recording started. Yeah, you can start now.
You're muted.
Yeah, hello. I think you're muted.
Okay, thank you. Yeah, I was muted. Okay. Okay, so first of all, I'll go through the motivation and some of the ad hoc approaches that were developed for to support this approximate computing. What we have witnessed is like further scaling was not possible. Scaling in the sense scaling of the size of the transistors. So as such, we have seen so far we have come till 3 nanometers or 2 nanometers or something like that, and still and still it's not much possible because of the limits of the physics. There has to be some different kinds of architectures with because we want to improve our chip performance area, and all these factors we would like to improve. And uh, and there is not much room to improve because we are facing this crisis because of the scaling. This approximate computing approach has been to support these kind of data driven applications, where we don't want perfect outputs from our chips. So we want some acceptable quality of outputs. So we want to tolerate some of the errors in it. So so because of that, and there's this concept of dark silicon. So the like major so even if we see the chip so the major portion of the chip at any point of time will be non-functioning because of the power saving, and that is like because of the cooling limitations, because there is not much room to cool down the chips, and there is that problem. So with that, these are like the main motivations that is driving this towards for the for the development of chips for these kinds of data driven applications. So we can have other factors from the data driven applications like machine learning, etc. So other factors there is noisy data is there. There is like edge computing is happening, and there can be there can be sudden increase in the load, etc. So all these are also driving this topic ahead. So far, the techniques that have been developed are simple techniques like precision scaling. So if you have like a 16-bit input, you just use an 8-bit and some do some quantization and try to make it work. But the problem is like it's not possible to go into the chip and resize each and individual register with the equal amount of precision that we want, and to optimize the chip in that manner. And that is why like all the sizes are 16 bits or 32 bits or something like that. So it's not possible to to individually scale all this. And so this is where some of the techniques in approximation come in handy. And the other problems are some of the other approaches that we have followed, there is something called as loop perforation. So in that we once we are compiling or something, we are performing some tasks. So in the loop we try to avoid some of the iterations. So it's like we have to decide based on the error constraint, like which of the iterations that we do not want to perform, so that the error is within certain limit. Other things is like sometimes there's like a cache miss or something. So you may want to keep on working, and like want to reduce that penalty, and so that you can approximate in that scenario. So there are like some of the approaches with respect to software that you can do about, you can go about for to solve this problem. But today I'll be mostly talking about approximate logic synthesis. So how do we like through some optimizations or something, how do we design these approximate circuits directly through, through some like for designing the circuits, we will use hardware description languages, etc. So what are the approaches that we can follow to directly go over mainly those techniques? So the first technique that for approximate logic synthesis that I have here is using an approximate standard cell library. So mostly you guys may not be familiar about the hardware design flow. So what we have is normally we have something as an RTL description, that will be a hardware description in the form of hardware description languages like Verilog or VHDL. And we there is this synthesizer and a technology mapper. So the job of it is like to take this and convert it into an equivalent circuit. So it uses something called as a standard cell library, where all the information, so it's like a building block. So it's like Legos. So you don't so in order to have something, you take small pieces, and then you build up your circuit from that pieces. So in that sense, this is a kind of a standard cell library that is like that will have some pre-characterized cells in it. So what we are trying to say here is like if we have some approximated cells in the same standard cell library, then we can have a much more optimized flow when we want to get the circuit from the code. So this is one approach of tweaking the standard cell library. So first of all, there are three important things that are followed in this approach. So the first is the design space reduction. So we cannot consider all the cells, because it is impossible to consider all the cells with because all these cells will be characterized with the different conditions. In the circuits, there will be a lot of factors that needs to be taken into account while characterizing a cell. For example, the cell that it is driving, that cell it is driven by. So all these factors needs to be considered while characterizing. So it's not possible to approximate all the cells, and there has to be some rule. The simple rule that is followed in this paper is like they take up like the energy consuming cells. So what are the cells which are consuming the most energy? So we'll try to approximate those cells. And here there is some kind of a truth table optimization that is being followed here. So each of the cells, so suppose this is a full adder cell. Full adder is nothing but you add 3 bits, so it makes a full adder. Okay. So this cell, so the truth table representation of the cell is given here. And we like to modify this truth table and have multiple representations of the same cell. So this cell is in turn represented by 6 cells, where each have varying degrees of approximation in it. So there are 2 bit errors here. There are like 4 bit errors in the truth table, and so on. So all these kinds of errors are purposefully introduced so that we have an approximate circuit. And this will in turn support whichever circuit you are designing using this approximate circuit. So if we go back to this diagram here, so this will pick an approximate standard cell from the library and try to meet this quality constraint that we have here. So this quality constraint will be defined by the user. So I mean give a particular some error matrix will be generated from this error matrix plotted here. So those error matrix whatever we are doing will be wasted. So it has to be within certain limit of any particular application that we are using for I mean using this circuit for. So maybe you are running an image application on the design circuit, and for that image application you can have some quality constraint, something like that. Okay, so this is then then after these cells are derived, we have to pick the cells. We have to pick whichever cell. Based on these constraint, and so multiple choices are there. So we get some kind of a Pareto curve here. So here the I mean this is like different types of adders are there. So for these adder circuits, it's been analyzed. So with different error metrics like the maximum error distance or mean error distance, and different error metrics are used, and the savings in area or the energy efficiency, etc., are are tabulated here. Oh, sorry, are given in the graph. Okay, so this is one of the technique that uses that uses a standard cell library. Okay, so the other technique is like without going into the flow of the chip design. So without going into the synthesizer, we want some technique to do the approximation at the Verilog level itself. So we don't want to synthesize anything, or we don't want any information regarding hardware. So there is technique where you can so from the Verilog description you can get an abstract syntax tree, and from this tree you can modify this tree and then generate an approximate description for the same circuit. So some transformations are required from while you are modifying this tree. So these transformations, I have listed some of them here. So what we can do is like we can use data type simplification. So like in Verilog, you will have some bit vectors, so we can reduce. This optimizer can take care of selecting the particular bit widths for different variables, etc. And some operation transformations like the addition operation can be replaced by some OR operation, etc., logical OR operation, and it will be approximate. But like some of the non-critical additions can be replaced in such a manner. So and there is like other arithmetic expressions, etc., can be represented, and there is like constant substitution is also possible, like variable to constant, because some variables are not that much changing. In for some a particular application, but they may be consuming some area in the circuit. So those can be, and then some loop transformation. So what we can do is like this loop, we can unroll it, and then we can do whatever transformations that we have done and so far, because it's not possible to do if we do a transformation here, just we replace it with an OR, will be incurring a very high approximation error. So we unroll the loop in the like before compiling itself, and then we do some transformations here. So this is like tried for some of the circuits, like a perceptron circuit, and some filters, and some fast Fourier transform circuit, etc. And a number of solutions are generated, and then some kind of an optimality or like a Pareto curve is plotted here for the different say the power consumption saving. So what is like power consumption in a chip is like defined by the how much switching is happening in the circuit. So we can target all these kinds of all these kinds of mm, nodes with some constraints that we have for approximation. Okay. So this is a totally Verilog kind of approach for approximating the circuit. Now, this is another approach where I mean, which is different from the other two, where we are using Boolean matrix factorization. So here in the first approach, we have used some sort of truth table optimization, but we have just done some, like, we have just manually just put I mean manually change the values or put errors in the truth table. But here we modify the truth table in such a way, like, so here the truth table was for a single function. I mean the single, so it's like sum and carry out. So so if we consider here, so here I mean the circuit represents like four inputs and there are four outputs. So for this kind of application, we try to pick circuits which have large number of inputs and large number of outputs as well. So this technique works better in that respect. And the other thing is, like, if the circuit is very large, it's impossible to apply this technique directly. We have to use some sort of circuit partitioning. So because if the number of inputs are large, this table will exponentially increase, and factorizing such a kind of a big Boolean matrix will not be possible. And Boolean matrix factorization is also not a very straightforward technique. It also uses some heuristics, etc., to get these factors. But the degree of factorization, we can control the approximation in this sense. So here, we have a truth table, and for all the possible combinations, we have the circuit functioning. And now we want to reduce the fourth output, say. So we factorize this into this. So there is I mean there is a predefined Boolean matrix factorization, I mean, uh, paper they are using for this. So I'm not going into much detail about the factorization part. So I just want to, I mean, show it here. So here we want to effectively like this I mean this matrix. So this entire table as a matrix, and we want to factorize into these two matrices. So effectively, while factorizing, we have reduced. I mean, we have reduced an entire column. So uh, so uh, so if we consider from this circuit to this circuit, this is a comparatively a smaller circuit. So it also takes the same number of inputs, but we have reduced. If we see from the output, there is kind of a logic cone that is forming here and here, like from this output, if we traverse back and all these connections, so all these connections are reduced while deriving this tree. But we have lost one output. So in order to get back that output, we can use a decompressor. We have to multiply with this matrix. So this matrix multiplication here is very simple, because we just have to or it, because 0 0 0. So it's just if we just multiply it and then add it, so this is like an or function only. So Mm, so, um, just we have to replace this decompressor by some network of OR gates. Wherever we are having one, that many OR gates will be required. So we are essentially reducing one output, and we are introducing few gates, and that logic cone that is there is getting replaced by a few gates. So that is in a sense some approximation. I mean, this that is in a sense some area savings. How, like, the approximation is coming in this factorization, because this factorization is not perfect. If we multiply these two matrices, then we get another matrix which will have some distance error. So if we compute the Hamming distance between these two matrices, we'll get for here we are getting 3, here we are getting 6, and so on. So these many bits will be in error. And so what they observe is like having distance was not a very good metric for optimizing, because some bits may have more value as compared to the other bits. So they used some kind of a weight function, and then they weighted this Boolean matrix factorization for their target quality of results. So with this weighting, they observe like there is significant improvement in the area saving for the same error. This is this optimization they achieved in this, and we can say like there is a lot of area savings and power savings, etc. Um, with this optimization, and so error introduced is also less comparatively. Like if you see so this is for a multiplier circuit. So if you see just like for uh, in some cases like just for like I don't know what is the exact units here, but like only a few error I mean for few error units we are achieving significant improvement in area. So it's like that. Normally, what we find in applications, so 5% degradation in accuracy will cause like 50% improvement in area or so. So just like a 5% degradation will get that much improvement. So it depends on an application. If it's willing to tolerate that much amount of inaccuracy, we can optimize it more. So here, as I explained, it is that factorizing part of the algorithm. And here, because for the circuits which are very large, we use some sort of circuit exploration, and we partition the circuit by some partitioning algorithm, etc. And then we select it in such a way so that this kind of this error is minimized when we are connecting these circuits, because we are individually approximating a number of circuits. So if you consider this circuit, and here say like each of the gate is itself a network of different gates. So each and every gate is getting approximated. So and the overall approximation error can get very huge. So it has to follow some threshold, and then that is being done here in this algorithm. Okay, so this is one of the approaches that was there. Um, and there is another approach where we use a pre-trained error network for doing the same thing. So the approach is almost the same for all of these, but the type of optimization we are doing, and the step at which this optimization is getting done, or this approximation is getting done, is different. So here, in order to so these algorithms were taking a lot of time. So in order to speed up these algorithms, what they did is like they use a pre-trained network for the error. So how did they train this network? It's like they used some well, first of all, they from the input description, they took out they represented the entire Verilog description into a graph. And from the graph, they introduced some of the errors deliberately, and then generated the data first. So they introduced lot of errors here and there, and then they kept noting all these errors, and whatever and the related information with these errors, like if there is some removal of some gate, what is the effect of the local error, what is the global error in the circuit, how is it changing, and and what are the if the number of outputs are getting affected, or the number of inputs are getting affected by the deletion of the particular node, and so on and so forth. Like all this information they have first generated from number of different circuits by introducing errors in different circuits. Um, on the data they train a network, and then they train a network to predict the error. So like they have reported sufficient accuracy in in predicting the error, and so on. And predicting the error is to drive the optimization algorithm. So it's not like we need to 100%ly with 100% we have to predict the error correctly only. So it's I mean, so it's good that they have like used this kind of an error network. And then so they just so while they are like this is the error network, but the normal optimization process they have kept it very simple. They are just removing some of the nodes from the circuit. So any new circuit can come up, and then they are removing some of the nodes from the circuit and then replacing them with the simpler gates, or then will give some more details. So there is like they are like selecting some of the based on some criteria. So like they are targeting for two different applications, that is power saving and area saving. So they want to get the nodes that have like I mean that are critical in terms of power. So they are consuming more power. That nodes they want to capture those nodes, and then they want to reduce that, and at the same time maintain the level of the error constraint. Uh, this is mainly done. I mean, in this algorithm. Um, so they also have reported sufficient, sufficient improvements in in terms of delay, sorry, in power and area. So I mean it's very small, but there are like some benchmark circuits are here, and then they have run it for these benchmark circuits and seen improvements. Okay, so this is okay. So this is one of the techniques, and then there is another technique. So this does not exactly come into approximation, but so this is LUT memorization. Okay. Suppose you the problem statement defined is like this. So you have like you want to get this Boolean function actually, this mapping function. So you are mapping a Boolean function, say an image, and then so based on the size of the image, we'll have the value of k, and then you just want to map it into a single classification of an image. And you just want to do all this directly without going into anything. Like you just want to do it in hardware. You just want to build a binary classifier using zeros and ones without considering the image or anything. Just zeros and ones you want to build it. And this will be a kind of an approximate circuit. It will not function as expected. It will function as expected, but only to some extent. Here the concept that they have defined is quite simple. Just they are selecting. So suppose this is x is the input and y is the output. Okay. So these are the different training examples. So this can be an entire image. Okay. So this is like for a very small for a small set of values. It's been demonstrated here. So so for this particular pattern, say 0 0 0, you are getting a 0, and again for 0 0 0 you are getting a 1. There is like you count for this particular pattern how many zeros you are getting, how many ones you are getting. So the same pattern, you note down the number of zeros and the number of ones, and that's all. You do that only, and if there are same number of zeros or you just put some random values. If say 0 0 1, uh, so it has okay, so 1 1, and then 0 1 0, there is nothing. Okay, so this is 0 0. Okay, so for getting this table, it's like that. So how many zeros are there, how many ones are there for that particular pattern. And then getting this function, you just take whichever is the highest. So 2 is the highest, so you take 1 here, and then and there is a tie here, both are zero, so you take any one. I mean, you either put zero or you either put one, so you don't care about that. Similarly, 0 1 1, you either put 0 or you either put 1 here. Similarly, you have a 0 dominating here, so you put a 0 here. So in that way, you learn some truth table. You learn some truth table from these training examples. So this is like a section of the training example, and from that section you have learned this kind of a truth table. So what they did is like they extended in the form of a for like a neural network. Like normally what we have is like a number of layers will be there, and there is like there are different computation units in between. So they have replaced all that with the lookup tables. So they are not performing any back propagation or anything. They just learning the truth tables. So just the learning process is also very simple based on the pattern only. So they have like just elaborated for another. It's just this is like a kind of a network instead of just a single truth table, because not possible to, because if this k is like 20,000, it's not possible to generate for 2 power 20,000 possible values, and then do this. So it's only natural to have this kind of arrangement where there are smaller truth tables. This network, so the network connections, they have just picked it random, so they didn't do anything to the connections. You just put random connections between these layers. And what they did is like this kind of an arrangement they use with the that gives a 0 or 1 in the first layer, and these many number of lookup tables are there. And these lookup tables, and each of these lookup tables, they have taken like 8 input lookup tables. So each are having like 2 power 8, so 256 possible input combinations. And these connections, so there are the circuit can have a lot number of connections, so based on the size of the image. So based on, so this is like so this is for the MNIST data set. So for the MNIST data set, they have like Hmm. For this, based on the size of the image for this, so this was just a black and white image. So for the size of the image, they have okay, what was I saying? Okay, yeah. So they have like these many LUTs with the each LUT having 8 inputs. And how many depends on the size of the image. This k value. So this k value they have got it around 784, I think. So these values, these connections are divided among these truth tables, all these truth tables that are there. Uh, so um, and then how this this learning is the same. So just counting the number of ones and zeros with respect to a pattern. So here 0 0 x1 is there. So the training examples are the same. So here 0 0 pattern is occurring 3 times. First, 3 times it's occurring, and the output is a 1 here. And similarly, it's occurring 2 times. Sorry, it's occurring one more time, and the output is here. So it's giving an output 0 for 1 time, and it's giving an output 1 for 3 times. 0 0 0 0 0 0 0. So here there is 3 and here there is 1. So in that way, individual tables are learned like this. So they also tried it for the CFAR data, CFAR 10 data set, but they didn't, because it's like just a binary classification. So just tried pairwise between different categories, and they found like reasonable good accuracies they can get with just learning of the truth tables without, without going into detail about designing anything, just by the truth tables. Just by a very simple algorithm, just measuring the number of zeros and ones, they are able to I mean, get this much accuracy. So what they did, whatever lookup table network they have, is like they mapped into an SOP representation, sum of product forms representation, and then they got Verilog from it, and then synthesized using an uninverted graph, and comparatively, like it's performing better. Like there is like it's based on this kind of network, it will have finite logic depth, etc. So based on that, it can be. So it's still in progress. This kind of work is still in progress. So anyhow, so okay, so these are some of the techniques for getting the approximate circuits directly. And then I'll like briefly talk about some of the issues that can happen with the testing of these approximate circuits, and why these approximate circuits can be insecure. Okay. So the testing problem is something what like how we are approximating. The testing problem is simply reverse of that. So once we design some chip and then we like ship out for manufacturing, at the time of manufacturing there can be a lot of errors that can happen in the chip design. So and then we test out the circuit by applying number of possible inputs, and then seeing whether the functionality of the circuit is correct or not. But how will we test these kinds of circuits, approximate circuits, because we have approximated them? So suppose the circuit is like a 2-bit adder, and we have not approximated a circuit. It would be easier to test by the addition functionality. So we can use some formal techniques, etc., and develop, and we can get some we will be able to test it easily. But what happens with some random approximations that we are applying to the circuit and all these things, and how will we able to test it? The best way is like, so all these test methodologies, what they use is like they use a fault model for the circuit. So all these fault models are nothing but whatever physical faults are that can happen in the circuit are combined into these fault models. So these fault models will normal scenarios that happens during manufacturing, etc. From these these fault models are applied on the circuit and checked. So in this fault models, in this paper they are proposing, like if we take the quality constraint to the fault model, then we will be able to classify the faults in the basis of approximation kind of redundant faults, and then which are not tolerable within the error constraint. So so if you see this truth table again, so there are a lot many input combinations are there, and there is and this is I mean this is the so this is the correct option. So here approximation you are using is like you are removing this pin. You are removing this connection, and in fact you are paralyzing this full adder and half adder operation, because this full adder this half adder does not depend on the full adder, and then you are like getting a better performance here. But with this approximation. So but what so the maximum error that can happen is like 2 bits of error. This is just an example. Normally this does not happen like this, but mm, this is your error constraint. So you do not want to have 2 bits of error, and then you apply the fault model. You apply the fault model, and you see that, oh, like these, like once the fault model is applied, the constraint, it's violating the error constraint. So you are for this Mm, so here for this combination you are it's really an error, and really an error. So this kind of chip should be stopped, because this is above your intended approximation. So these errors, although they are happening during manufacturing, this one bit, it's different from the approximate. It is within the approximation limit. So what they are proposing is like, so normally what we do is like we take care of these also. We don't want this one bit error, one bit error, one bit error, but this is within this constraint limit. So they are proposing like you can increase the yield of the circuits. Like why reject this circuit based on this one bit error? You are still within your tolerable limits of approximation. So since approximation, the advantage we can have is like, so we are manufacturing like 100 units, and out of this like 20 are faulty. And because of this approximation quality of the circuit, okay, with the 10, say among those 20 there are like 10 units which come into this approximation constraint, so they are also a bit fine. So they are proposing like why to reject all those. So this can improve the yield of the circuits, if you are willing, I mean if you are willing to approximate. So that is the main proposal in this circuit, I mean in this paper. And they are like translating this kind of approximation into a reduction in the faults that have to be taken into picture while checking for the yield. So if the number of faults are reduced, it's easier to check for those faults. It's easier to check the circuit, and thus testing of the circuit will become easier. In fact, so we thought we came from a point like the testing is in turn difficult, like with approximation, how we will test it, when to a point like testing has become quite easier if we are approximating the circuit. So finally, what is the problem that we have with approximate circuits is bit of the insecurity. So here, like a few examples I'm considering here. I'm just like, I have also not read much about, I mean, this aspect of hardware security, and there is IP privacy, and all these things. All these things are not my domain. So this is kind of an unlocking sequence. So this node will give an activation to this and this and this and this, and it will unlock some functionality in the circuit, say. But what happens is like you are approximating the circuit. So you are saying these nodes are pretty much same as these nodes, because this the error is tolerable between these two nodes. So you are willing to pass the circuit based on that. So the unlocking sequence, so there are a lot of unlocking sequences that have been developed in this method. So it's now becoming easy to unlock the circuit. So so in this way, like there can be some hardware locking that can be put in place, and that becomes very easy to unlock because of the approximation that you are doing to the circuit. So that is one point. Other points is like from the testing respect, so there are some attacks on the circuit which target this. The test circuitry, or it's that in that way. So since we are relaxing on that respect also, then there can be some there can be some malfunctioning of the circuit based on by exploiting in that area as well. So but like I am not very familiar with these ideas anyway, so I'm not going into much detail about it. Okay, so it completes my talk. So if you have any questions, please ask me. And um, thank you. Hello.
Yeah, so I had a question in chat. So you mentioned there is
Okay.
some sort of like redundancy
Okay.
which allows some
Yeah,
threshold.
I posted. Okay. Okay. I'll just go to the slide. Slider. Which slide?
Uh, you just mentioned there is some error threshold which is given by some sort of redundancy. Like where does that redundancy come in?
Redundancy in the application. So whatever application you're targeting, say speech application or an image application, so based on that application, whatever we how much you are willing to sacrifice, like how much classification accuracy or whatever your constraint is, like say you are getting like even after like classifying you are getting 80% accuracy, so in turn you are losing at that 20% accuracy. So that like in that way redundancy is coming. So and plus the other redundancy as I talked about is like we tend to keep all the precision etc intact while designing the circuits and all this, because to make our job easy. But that is like in turn contributing towards to a lot of area etc. So there are a lot of parts in the chip that we design that are not functional or are functional only at some point. So that can be avoided with approximation. So okay, maybe there is one case that happens in one, in a million. So why to waste a part of the circuitry for that? We can get around to it with some other approximations etc. So that is like a kind of redundancy that is coming.
Right. Okay. So it's in the application, not in the design part.
Yeah, in the application only. So whatever application you have, and from that you have to design the circuit. So from that you can. Yeah, any other? Yeah. So okay. So should I stop it?
Okay. So there are no other questions. I'll just stop recording. Give me a second.